Let's look at particles and waves, and this time blackbody radiation and Planck's constant. So all bodies radiate electromagnetic waves. In thermodynamics, we saw that radiation was one of the three forms of energy transfer, the other two being conduction and convection. And the equation for the power that was radiated, so Q over T is energy divided by time, so that's power, is equal to sigma E A T to the fourth. Sigma is the Stefan-Boltzmann constant, E is the emissivity, A is the surface area of the body radiating the energy, and T is the temperature measured in Kelvin, and that is raised to the fourth power. So the important part here is that the power radiated is a function of temperature to the fourth, where temperature is measured in Kelvin. So for instance, the sun's surface temperature is about 6,000 Kelvin, and it glows yellow. Betelgeuse, which is a star in the constellation Orion, has a temperature of only 2,900 Kelvin, and it glows red-orange. And in comparison to that, humans have a body temperature of about 310 Kelvin, and we don't glow. Max Planck was a physicist who calculated this blackbody radiation, and he plotted this graph. On the y-axis, we basically have the radiation intensity. The x-axis is wavelength. So remember that wavelength and frequency are inversely proportional. So as wavelength goes up, frequency goes down. So frequency is highest down here, lowest over there. And then these curves show us the temperature of the different bodies that were used for this. So at 3,000 Kelvin, you see that the intensity, the radiation intensity is lower. It increases at 4,000, it increases even more at 5,000. And the other interesting thing is that they peak at lower and lower wavelengths, which correspond to higher and higher frequencies. So the more temperature, the more energy was at lower and lower wavelengths, higher and higher frequencies. Now, in comparison to that, there is this curve here that's called the classical theory curve. And classical theory is what we have from thermodynamics, where we said that radiation increases as temperature to the fourth power. So here you just see the temperature increasing, whereas, the radiation intensity increasing, whereas here you just see it increasing and then decreasing. So from this plot, Max Planck concluded that the energy is NHF, where N is just an integer, F was the frequency, and he noticed that the proportionality constant between these was this quantity H, 6.63 times 10 to the negative 34th joule seconds, which is nowadays called the Planck constant or Planck's constant. Now, this N has to do with quantization, the quantity of HFs that form this energy. So when we have N equals 1, we have 1 HF, N equals 2, we have 2 HFs contributing to the energy. So N just has to do with the quanta corresponding to this energy.